Hello everyone, this is Vishwanath Hoga from the Department of Civil Engineering and welcome to the YouTube channel of Tonadara College of Engineering. In this session we shall discuss about the Benkel beam deflectometer which comes under the structure evaluation part. In the structure evaluation part of the pavement construction we will come across two types of evaluation, that is structural evaluation and the function evaluation. The Benkel beam deflectometer is one type of evaluation which comes under structural evaluation. This Benkel beam deflectometer is best suited for the flexible pavement. As you will note that the flexible pavement comprises of the four parts, that is subgrade, subbase, based on the varying course. And say for example, if the pavement is constructed for a CBR of 3%, and for 30 MSA, the CBR of the soil is found to be 3% and the pavement is designed for 30 MSA and the pavement thickness is come to be at 360 mm. What happens after certain decades due to the action of traffic or the wearing of the pavement course due to the construction of the pavement with inadequate materials, or due to the fast moving vehicles and wearing and tearing action of the structure, wearing and tearing of the wheels and the pavement surface, or due to the climatic conditions. Now the pavement section is designed for 360 mm. After the certain decay due to the action of climatic conditions and to the action of traffic, this 360 mm of the pavement thickness has been reduced to 300 mm. Now what we will do, we need to increase this 300 mm to 360 mm. What we will do, we design the overlay thickness which is need to be existing of the pavement thickness. So for example, this is the pavement thickness which is designed for, I'll take it as a design D, that is HD. HD is nothing but this is the thickness which is designed. This is the design thickness which comes for the CBR of 3% and 30 MSA. And after certain decades, the pavement has been deteriorated and the thickness has been reduced to 300 mm. And what we will do, in order to improve this pavement section from 300 mm to 360 mm, we come across the one pavement section called as the overlay thickness. This overlay thickness is need to be designed. This H0 need to be found out. Now what is this H0? H0 is nothing but the overlay thickness and HD is the total thickness required, and H0 HE is the total thickness of the existing pavement. Although this is the existing pavement, that is 300 mm. Next, overlay thickness H0 which is need to be defined, or it is need to be identified from the structure evaluation pavement, which helps in the improving of the pavement section. What will do? We'll go for Benkel beam deflectometer. This Benkel beam deflectometer works on a principle that when a well-compacted pavement section or one of the well-conditioned by traffic deforms elastically under each wheel load application, such that when a load moves away, there is an elastic recovery. As you can see that the wheel at the point 1, actually the wheel load at this point, you can see that there is a certain deformation of the pavement. This is the flexible pavement I am talking about. This is the flexible pavement. Whenever the tire is at the point 1, there is a certain deformation of the pavement, and whenever there is a movement of the vehicle, that is tire 1, now the position is moved to tire 2, you can see that is the recovery of the pavement, recovery of the elastic deformation. Now it is at a delta 1 and it is at a delta 2. In this case, the delta 2 is less than that of the delta 1, because the wheel load has been moved from the point 1 to point 2, because there is elastic recovery. Similarly, now the wheel load is at a point 2, there is elastic deformation of the pavement, and as you can see that in the third diagram, the point has been moved from point 2 to point 3 and there is an elastic recovery. In this manner the Benkel beam deflectometer works. This Benkel beam is a device which can be conveniently used to measure the rebound of the deflection of the pavement due to the dual wheel load assembly. And the wheel load assembly consisting of the standard tire pressure of 4085 and a truck loaded with a rear axle load of 8,170 kg used for deflection study only, and having the inflation pressure of 5.6 kg per centimeter. And this equipment consisting of slender beam of length 3.66 meter, which is provided at the bottom, and a frame at a distance of 2.44 meter from the probe end. What happens whenever this beam consisting of the beam having the probe end and the datum end, which will be rested on this rear axle and the front axle, and this will be inserted between the rear axle of the rear tires of the vehicle, which is used for the testing. One of the most things to be kept in remember is the loaded truck with a rear axle of 8,170 kg, which is used, and a dual wheel assembly of having the gross weight of 4,085 kg and having the inflation of pressure of 5.6 kg per centimeter square. And there is a difference between the contact pressure and the inflation pressure, and this Benkel beam consisting of having a center beam of 3.66 meter, which is provided atom frame with a distance of 2.44 meter. And what happens after inserting this Benkelman deflectometer? After inserting the Benkelman deflectometer to the rear axle of the loaded truck, what happens next? If the pavement section this is the pavement you need to be evaluated to the action of a Benkel beam deflectometer. As you can see that this is the truck, and this probe end or this Benkel beam is inserted between the rear axle or the rear tire of the rear tire of the truck, and it is kept in distance at the distance between the edge and the truck should be 0.9 meter and the 2.7 meter from the axle to axle. Then what happens? This is the stretch of a road which is need to be evaluated is first surveyed to assess the general condition of the pavement with respect to the ruts. There may be some ruts or undulation for the existing pavement due to the which has been caused due to the action of climatic action or due to the action of traffic. Then what we will do, the pavement stretches is classified into grouped into three classes, that is good, poor and fair. These are the three criteria which is used to classify whether the pavement construction, whether the pavement section which is evaluated is in a good condition, or it is in a poor condition, or it is in a fairer condition. The truck is moved from this point to this point. First, what happens? The truck is driven slowly parallel to the edges and stopped such that the left side of the rear dual wheel centrally placed over the first point for the deflection measurement. What happens? This truck will be moved, and this is known as a hungry spots or the dark spot. This may be either due to the ruts, spots, or to the wearing action. This part of the wearing action is nothing but the entire stretch of a road. This portion has been completely deteriorated, and we can see the subgrade or the subbase. This point, whenever the vehicle move to this point, whenever the dial gauge reading is stationary, the probe and the Benkel beam is inserted between the gap of the dual wheel assembly. This indicates the insertion of the Benkel beam. This indicates the insertion of Benkel beam between the rear wheel of the vehicle. Next, whenever this point or this probe is moved to this point, that is hungry point, which I mentioned as the ruts or dark spot, what they will do, whenever dial gauge reading is stationary or when the rate of change of pavement deflection is less than 0.025 mm per minute, the initial dial gauge reading, that is D naught, is noted. In this condition, we will come across 3 points, that is D naught is which is mentioned as the initial readings, DI intermediate reading, and DF as final reading. and these are measured when the dial gauge reading reads at a 0.025 mm per minute, and it should be maintained constant. After the three dial gauge readings, that is D0, DI and DF from the set of readings, one of the deflection point under the consideration. Similarly, the truck is moved forward for the next deflection point. The probe and the Benkel beam inserted. Procedure of noting the set of three deflection is observed is repeated. And we'll come across 3 points here. The first, the vehicle moves here and we'll note the DI point. Similarly, the truck moved to another point, we'll note it as the intermediate point. And after it reaches the final point, we'll take it as a D final. In these points, say for example, this is the stretch between the A and B. If the payment is evaluated for the payment A and B, which is being deteriorated, what we'll do, if this is the starting point and this is the end point, we can fix the number of points. Say for example, I need 15 points, 15 different deteriorated points or defect points. I can identify 15 different or deteriorated points from this pavement section, and I can measure all the deflection at each of the points. That is, what is the deflection at the first point, what is the deflection between the third point, what is the deflection between the seventh point, and what is the deflection between the ninth point. It is left to the evaluator whether he needs the deflection at each and every point of the identified 15 points, or he need to only the specification, either he alternate points or continuous points. It is left to the evaluator. After the evaluation, will come across there are two cases, that is DI minus DF is less than 2.5 division of the dial gauge of 0.025 mm 0.025 mm, then total D equal to 2 times the D0 minus DF divisions of 0.05 mm per minute. Next, there is a second case. If DI minus DF is greater than the 2.5 divisions, this indicates D equal to 2 times the D0 minus DF plus 2K plus into DI minus DF, where K is the where K can be determined by 3 equals to 3 times D minus 2E divided by F. Next, D mean. Then after getting the 15 points, after getting that 15 points out of the 20 points from each of the pavement section on which the area is to be surveyed or on which the pavement is to be evaluated for this structural action, we come across there are 3 parts, that is mean deviation and the standard deviation. The mean deviation is nothing but the summation of the total deflection observed on that particular point to the total number of points, and standard deviation, which is denoted by sigma, which equals to the square root of summation of d bar, that is d mean minus d divided by n minus 1, where n is the total number of points which is used for that particular pavement section. Now we shall discuss about the problem regarding the Benkel beam deflectometer. Let us consider the problem in the canine just to example 10.1, and it says the Benkel beam deflection studies were carried out on 15 selected points on a stretch of flexible pavement during the summer season using the dual wheel load of 4085 kg and the inflation pressure of 5.6 kg per centimeter per square. The deflection values obtained after making the necessary lag correction are given below. The traffic consisting of 750 commercial vehicles per day, and we need to determine the overlay thickness. If the temperature during the test was 30 degrees Celsius and the correction factor for subsequent increase in the subgrade moisture is 1.3, assume the annual rate of growth of traffic is 7.5% and adopt IRC guidelines. And these are the points, that is 1.40, 1.32, 1.25, 1.35, 1.48, 1.60, 1.65, 1.55, 1.45, 1.40, 1.36. These are the deflection points which is measured on that particular pavement. So the question says there is a pavement which is deteriorated and the Benkel beam deflectometer test has been carried out on that particular pavement. In that test, they have mentioned or identified 15 points. 15 points, and each of the deflection at these points are mentioned as 1.40, 1.32 as mentioned in the question. And they mentioned that there is a annual growth rate of 7.5 percentage. Annual growth rate is 7.5 percentage, and the moisture of the subgrade soil is 1.3. Now this pavement has been deteriorated. We need to design, or we need to give the overlay thickness. This is the existing pavement. Next, this is the overlay thickness. This is the existing pavement. This is the existing pavement on which they have carried out this test. This is the existing pavement they have carried out. On the existing pavement, they have carried out the Benkel beam deflectometer by identifying the 15 points, which is known as hungry points or the dark points of that particular pavement section. Now, this existing pavement has been deteriorated. We are asked to design the overlay pavement for this pavement thickness. After getting the data, we'll go for the first one, the mean deviation, standard deviation, taking into consideration of the IRC guidelines, and they also mentioned the temperature during the test was 30 degrees Celsius. Then what is the need of this 1.3 percentage and 30 degrees Celsius? Because the Benkel beam deflectometer is not independent of any of these factors. The Benkel beam deflectometer is dependent upon the temperature of the pavement and the subgrade soil of the pavement. If the subgrade soil of the pavement is wet, say for example, if the subgrade soil which is used in the construction during the test is wet, what happens? If it is wet, it can shows the more deflection. If it is dry, if the pavement section, while evaluating with the help of Benkel beam deflectometer, if it is dry, there is no large much deformation of that particular pavement as compared to the deformation which we get through the wet condition. We need to consider this 1.3% of the subgrade and 30 degrees Celsius of the pavement during this test, and necessary correction has to be applied for these two parameters. And they also said that the annual rate of growth of a traffic is 7.5 percentage. And they have also mentioned this is the traffic which is 750. This is the total vehicles for commercial vehicles per day for this particular pavement section. Now we need to design the overlay thickness taking into consideration of 750 commercial vehicle per day, and after making the correction for this moisture condition and for the temperature conditions. Now we shall solve the problem. This is the given data from the problem 10.1. 15 points has been identified on that particular pavement, and the vehicle which is used having the tire pressure of 4085 kg, wheel load of 4085 kg, and the tire pressure of 5.6 kg per centimeter square, and the present traffic is 750 commercial vehicle per day, and the temperature during the test was 30 degrees Celsius, moisture content was 1.3 percentage, and the annual rate growth is 7.5 percentage. And this is the points or the deflection which is measured on that particular pavement on which the Benkel beam deflectometer is carried out. First we'll go for the mean deviation, that is d bar equal to summation of d divided by total m. This summation of d is nothing but the total points, that is the deflection total points, where n is the total number of points, that is 50, 15, 20 or 25. This 15 points will, in this problem the n equal to 15, because on that particular pavement section between the A and B they have mentioned 15 points, that is varying from 1.40 to 1.45. Now we'll calculate what is the d bar, that is 1.40 plus 1.32. It is summation of all these things, that is from 1.40 to 1.45 divided by 15, which comes to be around a d bar as 1.45 meter, 1.45 mm. This is the mean deviation of that particular pavement section, one point which is under consideration between point A and B. This is the mean deviation of 1.45 mm. Then we'll go to standard deviation. In the standard in the textbook it is mentioned as sigma. You may take it as standard deviation, that is equal to sigma under square root of summation of d bar minus d divided by n minus 1. D bar is nothing but that is the mean deviation minus d. This d is nothing but each of the point, which you should consider each of the point, that is 1.40 to 1.45 in the calculation, which is shown in the further here. It is noted as 1.45, which is the mean deviation minus 1.40 whole square. Next, again the mean deviation, that is 1.45 minus 1.32, that is the second reading. Next, the third one is 1.45, again the mean deviation minus 1.25, which is third reading, and 1.45, it is the mean deviation, 1.35 the fourth reading, 1.45 the mean deviation, and 1.48 again the fifth reading, so on up to, you should go for up to the total number of 15 points. I'll repeat once again. This is d bar minus d. This d is the each and every point which is under the consideration of this deflection, varying from 1.40 to 1.32, divided by 15 minus 1, where n indicates the total number of points on that particular pavement, minus 1, which comes to be at 0.107. What happens? Character deflection dc, which comes to be as d bar plus sigma. The characteristic deflection is nothing but the mean deviation plus standard deviation. This characteristic deflection is the summation of mean deviation plus standard deviation, that is 1.45 plus 0.107, which comes to be at 1.557 mm. Then we need to apply the temperature correction for that particular pavement. Now the characteristic deflection of that pavement which is evaluated with the Benkel beam deflectometer is 1.557 minus 35. This is the standard temperature which is used, and 30 degrees Celsius is the temperature at which the test has been carried out. As you can see here, it is mentioned as 0.01. In the textbook it is mentioned as 0.065, 0.0065. Whichever you can consider it as, because both are correct. Either you consider as 0.0065 into and multiply this with this, it is correct. If you take 0.01 and multiply with this temperature correction, both are correct. It is the old edition and this is the new edition. 1.557 is the characteristic deviation, 35 degrees is the standard temperature for taking for the calculation, 30 degrees Celsius is the actual temperature at which the Benkel beam test was carried out, into 0.01 or 0.0065, whichever you may consider, it can be taken as correct, and it arrived to be 1.507 mm. Now you need to correct this mm for the subgrade moisture condition, that is 1.507 into 1.3, that is which comes to be at 1.905 mm. Then after this A value, this n equal to 2, and the design traffic as taken as 750. No, we need to design this traffic based on the actual commercial vehicle per day on that particular pavement section, plus 1 by r. This r indicates the annual growth rate. Next, n equal to 2, r equal to 7.5%, assuming it as an annual rate growth. P is 750, which is mentioned in the question. They have said the 750 is the commercial vehicle per day on that particular pavement section which is evaluated. It is given in the question, plus 1.075. This is 0.75 is the annual rate growth of traffic on that particular pavement section. Then This n plus 2 is nothing but we'll take it as overlay thickness as n equal to 2. Next, the annual, which comes to be at 1768 a commercial vehicle per day. Before, as you can see, there is a difference because the payment section which is constructed by taking this payment section was 750 commercial vehicle per day, and due to the economic growth of that particular locality or due to the transfer moving of the vehicle on that particular payment section, this 750 has been increased to 1768. This is the main reason to deteriorate for that payment section. Now, for the CVPD of 1500 to 1700 commercial vehicle per day, the IRC says the deflection should be taken as 1.0 mm. Now we'll design the overlay thickness for the commercial vehicle per day of 1768 with a deflection of 1.0 mm. There is an equation for the design of overlay thickness, that is h naught equal to 550 log to the base 10 dc divided by dA, which dc is comes to be as the corrected deflection of the subgrade with respect to the moisture and also with respect to the temperature. We'll consider as 1.95 mm in the design of the pavement thickness divided by dA. dA is nothing but the deflection which is given for the commercial vehicle per day for 1500, ranging from 1500 to 1700. We'll take it as a 1, and 550 to the log to the base 10 1 into 1.95 divided by 1, which is arrived to be 15.9 centimeter, whereas in the textbook it is mentioned as 16.5 centimeter. I have made a correction by taking I have made the calculation by taking as 0.01, but in the book they have gone for 0.0065. Both are correct. Either in the examination you can use for 0.01 or 0.0065. It is left to you. And DC is nothing but 1.95. It is 1.95. This is the total pavement thickness which has arrived by applying both the correction. Say for example, correction is nothing but both the temperature corrections and the moisture conditions, and will arrive at 1.95 to the total mm. 1.95 mm divided by 1, which comes to be as 159.51 mm, and divided by 10, which comes to be as 15.9 centimeter.